Hello, class. Today we're going to cover 4.3 logarithmic functions. Logarithmic functions are the inverse functions of exponential functions, so that's why we are going to be looking at them. Last time in 4.2, we looked at the natural exponential function, and this was the last problem we looked at, where I was investing $6,500 at a interest rate of 4.2%. And so I was able to calculate how much money I would have at the end of 25 years. So, which is fine and good. But sometimes we want to know, okay, well, if I have $6,500 and I want to end up with, let's say you want to end up with $25,000 at the end of a certain amount of time, how long would you need to let your money sit there in order for you to get to turn it into 25,000? So here we were solving for a, but there might be times when we're trying to solve for this exponent t. Okay, and so we're going to be looking at those types of situations, and what's going to happen is we will need the inverse function to solve for exponents. So that's where logarithmic functions come into play. They are the inverse functions of exponentials and will allow us to help to solve for time in that particular formula. Okay, so 4.3. Hopefully you're all keeping up with the homework. Once we're done with chapter 4, we will be taking a test. So here in 4.3, we will just be looking at an introduction to log functions. We'll take a look at its relationship to exponential functions. We'll look at how to evaluate them, and we'll look at how to graph them. Okay, so here we have the log function. Okay, so it turns out that the inverse of f of x, which equals to a to the x, and of course a is not 1, a is greater than 0, is defined to be y equals log a, base a of x. Okay, where if you have this log function, this log equation, then a to the y must equal x. Okay, these two forms are interchangeable. So again, note that a is greater than 0, a is not equal to 1, and x is greater than 0. Okay, so this x greater than 0, when we look at it in terms of the log equation slash function, so that basically means we're not going to be taking the log of a negative number. We're not going to be taking log of 0. Okay, not in this class. So log and exponential form. Okay, so what we're going to be doing is we're going to be looking at these two forms right over here that we just wrote down. So these two right over here. So let's just kind of have a closer look at these. So in the log equation, we have the letters y, a, and x. And if you look over here, in the exponential form, we also have the letters a, y, and x. Okay, so you should be able to go back and forth from one form to the other. Okay, so here in exponential form, this outside number y represents the exponent here in exponential form. Okay. Okay, so let's take a look at log form in this column, and then we'll take a look at exponential form over here in this column. Okay, so if I have the log of base 2, 8, equals 3, then I should be able to write this in exponential form. So that base 2 will also be the base for the exponential. So we're going to have a base of 2. And like I said up above, the exponent is this outside number. Okay, so it's going to be base 2, exponent 3, and that should equal the inside number, and which it does. 2 to the third power is 8. Okay, let's have a look at this one. Log base 5, 25 equals 2. Okay, so here the exponential form of this log would be, again, same base. If that's a base 5, we will also have a base 5. And the exponent over here is going to be the outside number, so 2. And that will equal the inside number, which is 25. And we see that that is true. 5 squared equals 25. Okay. All right. And see if you can do this one. Log base 16 of 4 equals 1/2. Okay, so go ahead and hit the pause button and go ahead and write the exponential form of that, and then come back to see if you got the same thing. So here you should have 16 to the 1/2 equals 4, which is true because an exponent of 1/2 is the same thing as the square root, and the square root of 16 is 4. Okay, very good. And go ahead and try this one. Log base 3 of 1/9 equals -2. Go ahead and hit the pause button, write down your answer, and come back. Okay, so here, base 3, so we will also have base 3 for exponential. The exponent will be -2, and it should equal 1/9, and it does because negative exponents will turn that into the reciprocal 1/3 squared, which is 1/9. Okay. Okay, so here, for the next 4 problems, let's go the other direction. So let's start with the exponential form, and let's see if you can go to log form. So over here, suppose that I have 10 to the third power equals 1,000. Okay, so 10 to the third power does equal 1,000. Okay, so if I want to write the log form of this, then we will use log. We use the same base that is used for the exponential. So the base over here is 10. So we'll have a little 10 over here for the base. And remember the exponent, this exponent 3, is the outside number. Okay, and that should equal 1,000 on the inside. Okay, so let's have another look. Suppose that I have this 4 to the 1/2 equals 2, which is true because 4 to the 1/2 is like saying square root of 4. Okay, so when we write this in log form, again, we use the same base. So the base here is 4. So the base here will be 4. The exponent, which is 1/2, will go on the outside. And that too will go on the inside. See how that works? Okay, so I'm going to have you try the next two. So here, suppose that I have 5 to the -3 equals 1 over 125. Go ahead and hit pause and write your answer in log form. Okay, so you should have gotten log. My base is 5. My exponent is -3. And my inside will be 1 over 125. Okay. And go ahead and try this one. Number 8, if you have 7 to the nth power equals m, go ahead and hit the pause button, write down your answer, and then come back. Okay, so base 7, so we will have log base 7. Exponent is n, so n is on the outside. And this should have m on the inside. Okay, so that's how you go back and forth between two forms. You might want to do this when you're evaluating logs. You might want to do this when you have to graph a log. Okay, so let's take a look. Evaluating logs. Okay, so suppose that I want to figure out the answer to this one here. Evaluate log base 3 of 27. Okay, log base 3 of 27. Okay, so we know that what should go on the other side is the exponent. So what we're actually trying to look for is, okay, well, if I look at this in terms of exponentials, then that answer should be the exponent of 3. That will give me 27. Okay, so can you think of an exponent? 3 to what power will give you 27? Okay, good. So you should have said 3. So then log base 3 of 27 is equal to 3. Okay. All right, let's have a look at another one. So when you're evaluating logs, you're basically looking for the exponent. So let's go ahead and evaluate this. Log base 25, and we get 1 over 5. Okay, this one's a little more trickier. So again, the answer to this needs to be a number that is the exponent for the base 25, such that we get 1 over 5. Okay, so here, it might be easier if you rewrite it. So you're trying to figure out 25 to what power equals 1 over 5. Okay, so this one isn't as intuitive or straightforward because you have the base 25 and you're trying to raise it to some exponent, and then you end up with a smaller number. Okay, so first of all, the fact that you go from 25 into 1 over 5 tells me that, okay, well, I probably have a negative exponent. Okay. And the fact that that way it takes the reciprocal. And 25 somehow becomes 5. So that happens with a square root. So this is going to be negative 1/2. Okay. Do you see how that would be negative 1/2? Because 25 to the negative 1/2, the negative takes the reciprocal, turning it into 1 over 25. And then that 1/2 is the same as a square root. So the square root of 25 would be 5. Okay. Okay. Go ahead and try this one. Go ahead and evaluate log base 4 of 1 over 64. Okay, so you're trying to figure out what that equals. And so remember, you're trying to figure out 4 to what exponent will give you 1 over 64. Okay, so go ahead and hit the pause button and try to work that out. Okay, so we go from 4 to 1 over 64, so probably need a negative exponent there. Okay, and then the 4 becomes a 64, which is bigger, so can you think of an exponent? 4 to what power is 64? Third power. Okay, very good. So we get negative 3 here. Okay, so we have, so that's evaluating logs. You're basically trying to figure out the exponent that works. So just try to keep in mind some fraction exponents, like 1/2 if you're trying to do square roots, or 1/3 if you're trying to do cube roots. Okay. All right, and then we have some properties of logs. These properties are that we're going to learn here in this section are more of the intuitive properties of logs. And then in the next section, we're going to take a look at more properties of logs, which aren't so intuitive. Okay. All right, so the first one. Let's see if you can evaluate these. Log, and you have any base, any legal base, okay? And you have 1. So can you think of an exponent? A to what exponent will give us 1? Okay, you should have said 0. A to the 0 equals 1. So this first property here basically says that if whenever you're taking the log of 1, it's going to be 0, no matter what your base is. Okay, number 2, suppose that you have this one. Log base A of A. So you're taking the log of A, base A. So can you think of an exponent? A to what power will give you A? You should have said 1. Okay, so this property is basically saying that if you're taking the log of a number and that number is the same as the base, well, it's going to be 1. Okay, and what about this one? Log base a to the x. Okay, so here, a to what power will give you a to the x? Should be x, right? A to the x is equal to a to the x. Okay, and this fourth one here, this one is not as intuitive. So let me explain this one. So this one says a to the log base a of x equals x. So at the very beginning of the section, I talked about how exponentials and logs are inverse functions of each other, right? And if you remember, we have that property that says, okay, well, f and g, if f and g are inverses of each other, then f circle g. When you do that composite, you get x. And when you do the composite the other way, g circle f, you also get x. So that's where this number 4 comes from, okay? Because if your f function is, let's say f is a to the x, and g is log a x, right? Okay, so when you do f circle g, these are inverse functions of each other, so you should get x, right? And f circle g means you're taking the g function, which is this one right over here, plugging that in for x in the f function, which is right over there. Okay, and that's what we get over here on this left-hand side. It's the composition function f circle g. And we know that since they're inverses of each other, the composite function of inverse functions should always give us x. And that's how we get x here. Okay. This one is going to be handy later on when we start solving log equations. Because you see here, this is almost like, oh, it's like they look like they cancel out, but it's not so much that they're canceling out. Okay, so, but you can use that sort of visual concept when we're solving for logs, so that if I'm trying to solve this log base 3 of 2x equals 7, right? Well, I can rewrite that left side using number 4. Okay, and then that should equal 2x. Okay, but we'll do that. We'll do more of this later on. You don't have to worry about that. So you just need to be familiar with these 4 intuitive properties, with an exception of number 4 being intuitive. The other 3 should be. Okay. All right. So if you take a look at your calculator, so if, let's say you were trying to do this, log base 2, 5, right? You don't have to copy this right now. Just pay attention here. Log base 2 of 5, right? Well, 2 to what power is 5? There is no particular number, right? We end up with a decimal because 2 squared is 4, and then 2 cubed is 8. So 2 is too small, 3 is too big. So it's going to be, the answer is going to be somewhere between 2 and 3, some decimal number. Okay, now if you take a look on your calculator, you'll notice that you don't have this. You don't have log base 2. Okay, what you do have is, so if we wanted to do that, or if I wanted to do this, or if I wanted to do this one on the calculator, I don't have log with these different bases, right? So what happens is you have 2 buttons on your calculator. You have, you only have 2. You have the common log, Okay. And that button looks like this. It'll either look like this. Okay, log. So if you do log of x, that means common log of x. Or it might look like this with a base 10. Okay, so you have either log with no base, it's blank. No base means it's common log, which is base 10. Okay, you have that one. Okay, so just put a note there. No base means base 10. Okay, and then we have what's called the natural log. You also have this one on your calculator, but these are basically the only two that you have. The natural log, which looks like this, ln. Okay, so look for that button on your calculator. And ln means the same thing as this, log with a base e. Okay, and if you recall from the last section, e is Euler's number, which is 2.718. Okay, goes on forever. Okay, so this here, ln, that's an ln for natural log. Natural log because what happens is a lot of these problems in nature can be solved or modeled using the natural log, like population growth, the way viruses grow, the way radioactivity decays. Okay, so natural log of x, this means base e, which is roughly 2.718 ... Okay. All right, so these are the two that you have on your calculator. You have the common log base 10, and you have the natural log base e. We'll talk about how to evaluate these problems that I just put down here in the next section. Okay, but for now, you just need to worry about log base 10 and log base e. All right, so let's take a look at graphing. So there's different ways to go about this. So you can plot the parent function, y equals log whatever base they're using, then shift. All the shifting is, again, still the same, those transformations. Plus 3 means up 3, minus 3 means down 3, etc. Okay? Or you can rewrite as an exponential, then graph it, then graph. Okay. And one thing to note, you do have a vertical asymptote. At x equals 0 for the parent function. Okay, which is going to be y equals log whatever base you're using, x. Okay, that's the parent function. Okay, so let's take a look at an example here. let's go ahead and graph y equals log base 2 of x. Okay, so I'm going to use the method of changing this to the exponential form. Okay, and so we said that we have a vertical asymptote at x equals 0. Okay, so right here, we start off with that. If we have any transformations, then this will also shift left or right along with the graph. Okay, so I will go ahead and rewrite this this equation as the exponential. Okay, so here the exponential would be base 2 to the exponent y, and it should equal that x. Okay, so here, this might be a little bit easier to graph. Okay, and here, what's easier to plug into this function? X values or y values? So hopefully you said y values. Okay, so I'm going to plug in 0, and I'm going to plug in 1, and I'll plug in -1. Okay, so here you can see it's easier to choose to plug in y values. Okay, all right, so let's go ahead and find the x coordinate. All right, so when I plug in 0, what's 2 to the 0? 1, good. When I plug in 1, what's 2 to the first power? 2. And when I plug in -1, what's 2 to the -1? 1/2. Okay. All right, so we have a point at 1, 0. So a point there at 1, 0. A point at 2, 1. Ah, okay, a little off there. Let me fix that. Okay, 2, 1. And then over at 1/2, -1. Okay, and so what happens is this is sort of like a sideways exponential graph. Okay, and that's basically it. And then if you do have anything added or subtracted or multiplied, you would take care of those transformations the same way. So had this said x plus 2 inside the parentheses like that, that would be a shift 2 to the left, right? And then if it said this, it would take this same graph and also shift it down 3. Okay, so the transformations are still the same. Okay, let me erase that so it doesn't look like it was the problem we were supposed to graph. Okay. All right. So let's take a look at one that has some shifting. Let's go ahead and graph y equals log base 3 x minus 1 plus 2. Okay. So again, the parent function here would be y equals log base 3x. Okay. So that's your parent function. And all of those other things are just transformations, right? Okay, like this one over here is up 2, takes your parent function and shifts it up 2. This one over here takes your parent function and shifts it 1 to the right. Okay. All right, and so I'm going to take that parent function and rewrite it as an exponential. So base 3 to the y exponent equals x. Okay, and now at this point, I want you guys to go ahead and hit the pause button and see if you can do this on your own. Okay, go ahead and pick your points, set up your vertical asymptote, and plot your parent graph, and then do your shifting. Okay, so go ahead and hit pause, give that a try. There we go, and come back. Okay, so this is what you should have gotten. You take those 3 points that you got from your table of values for the parent function, and then you just shift those 3 points to up and 1 to the right. Okay, so that is basically it for the introduction to logs. And the next section, 4.4, we will take a look at the laws of logs. And that is what we're going to be using when we solve some of the log equations. Okay. All right. If you have any questions, make sure you text me, email me, request for a Zoom meeting, and make sure you keep up with the homework. Enjoy your day.